Welcome to our YouTube channel, where artificial intelligence meets the world of computer hardware and networking. In today's video, we have an exciting topic lined up for you: AI teaching computer hardware and networking in depth. Part 1. Computers have become an integral part of our lives, and understanding their inner workings can be a fascinating journey. With the advancements in artificial intelligence, we now have the opportunity to explore computer hardware and networking in a whole new way. So, let's get started. The invention of the computer was a result of the collaborative efforts of many individuals over time. Here are some key contributors to the development of the computer. Charles Babbage, 1791 to 1871, known as the father of the computer. Babbage conceptualized and designed the analytical engine, an early mechanical general-purpose computer. Although the analytical engine was never fully built during his lifetime, it laid the foundation for modern computing principles. Ada Lovelace, 1815 to 1852. Lovelace, a mathematician, is credited with writing the first algorithm intended for implementation on Babbage's analytical engine. She recognized the potential of computers beyond mere calculations, envisioning them as capable of processing symbols and creating music. Konrad Zuse, 1910 to 1995. Zuse, a German engineer, is known for building the Z1, considered the world's first programmable electromechanical computer. He continued to develop more advanced computer models, including the Z3, which is often regarded as the world's first fully functional programmable computer. Alan Turing, 1912 to 1954. Turing, a British mathematician and computer scientist, made significant contributions to the theoretical understanding of computing and artificial intelligence. His work on the concept of a universal machine laid the foundation for modern computer architecture and the idea of stored programs. John Atanasoff and Clifford Berry, 1903 to 1995, 1918 to 1963. Atanasoff and Berry collaborated on the development of the Atanasoff-Berry computer, ABC, in the late 1930s. The ABC utilized electronic switches and binary arithmetic, making it one of the earliest electronic digital computers. J. Presper Eckert and John Mauchly, 1919 to 1995, 1907 to 1980, Eckert and Mauchly are credited with designing and building the ENIAC, electronic numerical integrator and computer, in the 1940s. The ENIAC was a large-scale electronic computer that introduced the concept of using vacuum tubes for computational purposes. These individuals played pivotal roles in the early stages of computer development, but it's important to note that computer technology has been refined and advanced by countless engineers, scientists, and inventors over the years. The modern computer is a result of the collective efforts of many innovators and pioneers in the field of computing. Computer generations refer to different periods in the history of computing, characterized by significant advancements in technology and architectural design. The concept of computer generations helps classify and understand the evolution of computers over time. Here are the commonly recognized generations of computers. First generation, 1940s-1950s. Vacuum tubes. Early computers used vacuum tubes for circuitry and data processing. Examples: ENIAC, UNIVAC I, EDVAC, EDSAC. Second generation, 1950s-1960s. Transistors. Transistors replaced vacuum tubes, leading to smaller, more reliable, and faster computers. Batch processing. Computers used batch processing, where multiple jobs were submitted together for processing. Examples: IBM 1401, IBM 7090, CDC 1604, UNIVAC II. Third generation, 1960s-1970s. Integrated circuits, ICs. Integrated circuits brought multiple transistors onto a single chip, increasing computing power and reducing size. Operating systems. Time-sharing and multiprogramming became common, allowing multiple users to share computer resources simultaneously. Examples: IBM System 360, DEC PDP-11, CDC 6600, IBM System 370. Fourth generation, 1970s to 1980s. Microprocessors. The invention of microprocessors revolutionized computing, placing the CPU on a single chip. Personal computers, PCs. The introduction of PCs made computing accessible to individuals and businesses. Examples: Apple II, IBM PC, DEC VAX, Cray 1. Fifth generation, 1980s present. VLSI technology. Very large-scale integration, VLSI, allowed for even greater transistor density on chips. Parallel processing. Computers started utilizing parallel processing techniques for improved performance. Examples: IBM AS400, Cray XMP, DEC Alpha, Intel Pentium, AMD Ryzen. 6th generation, present and beyond. Advanced microprocessors. Ongoing advancements in microprocessor technology, including multi-core processors, increased clock speeds, and improved power efficiency. Artificial intelligence, AI technologies and machine learning algorithms are becoming increasingly integrated into computing systems. Examples: Intel Core i7, AMD Ryzen 5000 series, Apple M1. It's important to note that the boundaries between generations are not strictly defined, and advancements can overlap. Additionally, newer generations often build upon the innovations of previous generations, leading to incremental improvements in performance, power efficiency, and functionality. The evolution of computer generations has led to the development of increasingly powerful and versatile computing devices, shaping the modern technological landscape. Computers are complex machines that play a central role in our daily lives. They are used for various purposes, including communication, data processing, entertainment, and problem-solving. In this detailed overview, we'll cover the basics of computers, including their components, operation, and key concepts. Components of a computer. Central Processing Unit, CPU. The CPU, or Central Processing Unit, is the primary component of a computer that performs most of the processing and calculations. It is often referred to as the brain of the computer. The CPU interprets and executes instructions, performs arithmetic and logical operations, and manages data movement within the computer system. The CPU is composed of several key elements. Control Unit, CU. The control unit is responsible for managing and coordinating the operations of the CPU. It fetches instructions from the computer's memory, decodes them, and controls the flow of data between various components. Arithmetic Logic Unit, ALU. The ALU is responsible for performing arithmetic operations, such as addition, subtraction, multiplication, and division, and logical operations, such as comparisons and Boolean operations. It handles the mathematical and logical computations required by the computer programs. Registers. Registers are small, high-speed storage units within the CPU. They hold data that the CPU is currently working on or data that needs to be stored temporarily during processing. Registers provide fast access to data, allowing the CPU to perform operations quickly. Instruction Set Architecture, ISA. The ISA defines the set of instructions that the CPU can understand and execute. Each instruction represents a specific operation that the CPU can perform, such as loading data from memory, storing data, or performing arithmetic operations. Different CPUs may have different instruction sets. The CPU works in a cycle called the fetch, decode, execute cycle. Fetch. The CPU fetches the next instruction from the computer's memory based on the program counter, PC, that keeps track of the current instruction's location. Decode. The CPU decodes the fetched instruction to understand what operation needs to be performed. Execute. The CPU carries out the operation specified by the instruction, using the ALU, registers, and other components as needed. This could involve performing calculations, accessing memory, or transferring data between different parts of the system. Repeat. After executing an instruction, the CPU moves to the next instruction by incrementing the program counter, and the fetch, decode, execute cycle continues until the program's execution is complete. The speed and performance of a CPU are determined by factors such as clock speed, the number of instructions it can execute per second, the number of cores, which allows for parallel processing, cache memory size, and the architecture of the CPU. CPUs come in different types and families, including those made by Intel, AMD, ARM, and other manufacturers. They are a crucial component in determining the overall capabilities and performance of a computer system. Intel Processor. Intel is a leading manufacturer of processors for computers. They have produced various processor families over the years. Here are some notable types of processors from Intel and their respective generations. Intel Core processors. Intel Core i3, entry-level processors suitable for basic tasks like web browsing, word processing, and light multitasking. Intel Core i5, mid-range processors offering a good balance of performance and power efficiency. suitable for gaming, multimedia, and general productivity tasks. Intel Core i7, high-performance processors with higher clock speeds and more cores. Ideal for demanding tasks like video editing, 3D rendering, and gaming. Intel Core i9, the most powerful consumer-grade processors from Intel. They offer exceptional performance for demanding tasks and heavy workloads. Intel Xeon processors. Intel Xeon processors are designed for professional workstations and servers. They are optimized for tasks such as data analysis, scientific computing, virtualization, and running enterprise-level applications. Intel Atom processors. Intel Atom processors are designed for low-power devices, such as netbooks, tablets, and embedded systems. They prioritize power efficiency over high performance. Intel Pentium and Celeron processors. Intel Pentium and Celeron processors are budget-friendly options suitable for basic computing tasks like web browsing, email, and light office work. Each processor type has gone through multiple generations, with each generation offering improved performance, power efficiency, and new features. Intel typically releases a new generation of processors every year or two. Some notable generations include Intel Core processors. First generation, codenamed Nehalem, 2008. Second generation, codenamed Sandy Bridge, 2011. Third generation, codenamed Ivy Bridge, 2012. Fourth generation, codenamed Haswell, 2013. Fifth generation, codenamed Broadwell, 2014. Sixth generation, codenamed Skylake, 2015. Seventh generation, codenamed Kaby Lake, 2016. Eighth generation, codenamed Coffee Lake, 2017. Ninth generation, codenamed Coffee Lake Refresh, 2018. 10th generation, codenamed Comet Lake, 2019. 11th generation, codenamed Tiger Lake, 2020. 12th generation, codenamed Alder Lake, 2021. Intel Xeon processors. Intel Xeon processors have their own naming schemes, and their generations are often aligned with the corresponding Intel Core processor generations. These are just a few examples of Intel processor families and generations. Intel continues to innovate and release newer generations with improved performance, efficiency, and features to meet the evolving needs of computing. AMD processor. AMD, Advanced Micro Devices, is another prominent manufacturer of processors. Similar to Intel, AMD has produced various processor families with different capabilities and performance levels. Here are some notable types of processors from AMD and their respective generations. AMD Ryzen processors. AMD Ryzen 3, entry-level processors suitable for basic tasks and budget-conscious users. AMD Ryzen 5, mid-range processors offering good performance for gaming, multimedia, and productivity tasks. AMD Ryzen 7, high-performance processors with more cores and higher clock speeds, ideal for demanding workloads and content creation. AMD Ryzen 9, the most powerful consumer-grade processors from AMD, designed for heavy workloads, gaming, and professional tasks. AMD Threadripper processors. AMD Threadripper processors are high-end desktop processors targeted at professionals, content creators, and enthusiasts. They offer exceptional multi-threaded performance and support for extensive multitasking. AMD EPYC processors. AMD EPYC processors are server-grade processors designed for data centers and enterprise-level computing. They provide high core counts, advanced security features, and excellent performance for demanding server workloads. AMD Athlon and Sempron processors. AMD Athlon and Sempron processors are budget-friendly options suitable for entry-level desktops and basic computing tasks. AMD processors have also gone through different generations, each introducing improvements in performance, power efficiency, and features. Some notable generations of AMD processors include First generation Zen architecture, codenamed Zen, 2017. Second generation Zen Plus architecture, codenamed Zen Plus, 2018. Third generation Zen 2 architecture, codenamed Zen 2 inches, 2019. Fourth generation Zen 3 architecture, codenamed Zen 3 inches, 2020. Fifth generation Zen 3 Plus architecture, codenamed Zen 3 Plus, expected in 2022. AMD has been consistently improving its processor lineup, providing competitive options across different price points and performance requirements. Each generation brings enhancements in core architecture, instruction set optimization, cache hierarchy, and overall performance. It's important to note that AMD's processor nomenclature and generations may differ from Intel's. It's always recommended to check the specific model and generation of a processor to understand its capabilities and performance characteristics. ARM processor. ARM, Advanced RISC Machines, is a type of processor architecture commonly used in mobile devices, embedded systems, and low-power applications. Unlike Intel and AMD processors, ARM processors are typically not sold directly to consumers but are licensed to other companies for customization and implementation in their products. Here are some notable ARM processor families and their generations. ARM Cortex-A series. The Cortex-A series processors are designed for high-performance applications such as smartphones, tablets, and laptops. Cortex-A7, an energy-efficient processor with a focus on power efficiency and cost-effectiveness. Cortex-A9 provides enhanced performance over the Cortex-A7, suitable for mid-range mobile devices and smart TVs. Cortex-A15 offers improved performance and scalability, targeting high-performance smartphones, tablets, and network infrastructure. Cortex-A53, a power-efficient processor widely used in smartphones and other low-power devices. Cortex-A57 provides higher performance and power efficiency compared to the Cortex-A15, suitable for high-end smartphones and servers. Cortex-A72 offers increased performance and power efficiency over the Cortex-A57, targeting premium mobile devices. Cortex-A73, designed for high-performance mobile and consumer devices, offering improved power efficiency and performance. Cortex-A75 provides enhanced performance for high-end smartphones, laptops, and other devices. Cortex-A76 features architectural improvements for increased performance, targeting premium mobile devices and servers. Cortex-A78, designed for premium mobile devices, offering improved power efficiency and performance over the Cortex-A76. ARM Cortex-R series. The Cortex-R series processors are designed for real-time applications, including automotive systems, industrial control, and storage devices. Cortex-R4 provides real-time capabilities with low latency and deterministic performance. Cortex-R5 offers improved performance and advanced features for real-time applications. Cortex-R7 provides higher performance, reliability, and safety features for demanding real-time systems. Cortex-R8, designed for high-performance real-time systems with advanced safety and security features. ARM Cortex-M series. The Cortex-M series processors are designed for microcontrollers and embedded systems, focusing on low power consumption and cost-effective solutions. Cortex-M0, a low-power processor suitable for entry-level microcontrollers and low-cost devices. Cortex-M3 provides increased performance and advanced features for a wide range of embedded applications. Cortex-M4 offers additional features like digital signal processing, DSP, instructions and floating-point operations. Cortex-M7 provides enhanced performance and advanced features for demanding embedded applications. Cortex-M23, designed for highly efficient and secure microcontroller applications. Cortex-M33 offers increased performance, advanced security features, and support for trust zone technology. Cortex-M55 combines efficient processing with advanced machine learning capabilities, targeting IoT and AI applications. ARM continually evolves its processor designs, introducing new generations and architectural enhancements to meet the demands of various markets and applications. It's worth noting that ARM processors are often customized by licensees, who may incorporate additional features and optimizations based on their specific requirements. That's it for today's video. If you enjoyed it, don't forget to hit that like button and subscribe to our channel for more exciting content. As always, if you have any questions or suggestions for future videos, please leave them in the comments below. Thank you for watching, and we'll see you in the next video part 2.